Welcome to the course in discrete data analysis. You may be familiar with the concept of regression and the use of techniques like least squares to estimate the regression line for the case when we have a continuous outcome. In this course, we are going to generalize the concept of regression to the case when we do not necessarily have a continuous outcome, but can also have outcomes which may be discrete. So two very common examples of discrete outcomes are binary responses, where we observe the response say yes or no for each of a sample of individuals. The second is the example of counts. So mortality, the total number of births, etc., the total number of accidents, these are all common examples of counts. The course is organized in this manner. We will begin with a very simple situation, which is a fundamental unit of learning in many applications such as epidemiology. This is the 2x2 table. Using a 2x2 table, which you will observe arises when we have one covariate which is binary and one outcome which is binary. We will define some very simple measures of association such as the risk difference, the risk ratio, and then extend this to odds and the odds ratio. We will compare these outcomes. We will see that the odds ratio has certain advantages over the risk ratio. Then we will move on to the concept of ordinal and nominal association. Now we might have categorical data where the categories cannot be ordered. So say for example hair color, eye color, where there is no natural ordering. Or we may have categories which are essentially ordered. So for example, we could have age categories, we could have the degree of support for a proposition. We will look at some summary measures of association for the case when we have ordinal data. Having done this, we will then move towards establishing a general framework for discrete regression models. This is called the GLM, or the generalized linear model. A generalized linear model is applicable not only to the case when we have binary or count data, but in general to a large family which arises from the one parameter exponential family of distributions. Thus, the linear normal regression, which you know so far, is also a special case of GLMs. So we will move from the theory of least squares to the theory of likelihood-based inference. We will do a quick recap of likelihood-based techniques and then see how to apply these techniques to the case of a generalized linear model. We will see that unlike for the continuous outcome case, the score equations here have no well-defined solution, no obvious solution. They're just implicit equations in our parameters of interest, and we will establish numerical algorithms based on Newton-Raphson to maximize the likelihood. Having looked at the GLM, we will look in more detail in three particular very common examples: the logit model, the probit model, and regression for count data. The first two can be motivated from an econometric framework by an approach called the binary choice approach. After looking at this, we will look at some case studies in R and then move on to the case when the outcome is polytomous. This means that it is still categorical, but the number of categories is more than 2. In such situations, we will extend the concept of logistic regression and see that there are different techniques depending upon whether the outcome is nominal or ordinal. Finally, we will look at some extensions of the GLM. These can be in various directions. The first is the concept of over-dispersion and under-dispersion. These are situations where the assumptions made by the one-parameter exponential family do not necessarily hold for empirical data. So say, for example, we're observing a count and we have a situation where the mean and the variance appear to be different. Here, an accepted framework to use is that of quasi-likelihood estimation, which we will visit. We will then move on to the idea of mixed models and generalized mixed models. These are known as GLMMs, or generalized linear mixed models, in the literature, and a case study using GLMMs for longitudinal data. We shall conclude the course by looking at another extension to GAMs, or generalized additive models, which consider the case when the dose-response relationship is no longer linear and we do not want to impose any prior parametric assumptions about the nature of the nonlinearity.